Well, thank you, Jensen, very much for the kind introduction, and good afternoon, everybody. So this talk is not about digital twin. If you're looking for digital twin, that's something different. And I'm here to present this topic on behalf of my PhD student. Yuxi is supposed to be online somewhere, being able to answer the questions. In the case that doesn't work out well, feel free to reach out to us, and we will be more than happy to follow up. So here's the introduction. Utility network. This is kind of some very interesting problem. It's a niche point that we are dealing with. So utility, especially underground pipes, they belong to the type of infrastructure. Once you bury them, you intended to forget about them, right? The only time that you think of them is there's a problem. Either there's a cable, there's a network service interruption, there is an electricity outage, there's a wind storm coming in and blow off your utility lines, etc., etc. Then it becomes the problem. The specific area we are looking at is called utility strikes. So utility strike means that when you're doing construction, you unintentionally hit underground pipe, right? Nobody wants to hit the underground pipe. But if you unintentionally you hit the ground pipe, that becomes a big problem. So the problem is very significant if you have to think about the massive underground infrastructure we have, in the United States and worldwide, and also looking at the frequency of utility strikes. In the United States alone, it's one strike every minute, right? Average every minute, and it kills thousands of people, hundreds of people, thousands of injuries, and billions of financial losses. So and the underground situation is very complicated. And my group has been working in this domain for past 15, 16 years, and just trying to figure out what's the best way of dealing with that one. So from the practical perspective in the United States, American Society of Civil Engineers, they categorize the utility data in four quality levels or development levels into A, B, C, D. And apparently D refers to the utility records, and the C refers that you go to the site, make a site visit, and make a confirmation. So for example, even looking at this indoor space, you look at a bunch of outlets on the ground, you know that you're going to have some lines running underneath and connecting these things together. So level B, this is the part that we talk about the geophysical methods. You can run, geo and ground penetrating radar to look into the ground and tell you where your pipes are located. And of course, the most accurate and the most expensive approach is actually to dig a hole and trying to expose the underground utility pipes, and that's called quality A. So, which everyone can understand, that's going to be very expensive to do so. So here's our vision towards a safe underground utility environment. So we are looking at a real-time utility mapping and visualization system. So put that into a nutshell, what we are trying to do is take all the contextual cues. You have light poles, you have manholes, those things that are visible, available to you, and then you can take them into consideration. And you can also leverage any of the existing records. And once you have them, that goes to the very nice way of getting into our geophysical methods that you can run sensors. And of course, we are not going to be avoiding IR algorithms and the sensing technologies and so on and so forth, and put them into cloud. And once you have the data during excavation, you can actually visualize. You can bring the real-time information to the field operators, get to see where utilities are, and then be able to avoid hitting them. So this particular topic is looking at one specific step called the topology inference. So the main idea is that we know some of the point locations, such as the outlets over here, such as the manholes in the field, such as light poles. So what we would like to do is that, can you take all these available cues and then complete the topological network so you know which where your links are, links exist. Now, thinking about underground pipes for gas, for water, for sewer, for storm water, they're all rigid structures, right? So it's not like electricity lines you can meander around. They becomes a little bit more straightforward. So that is our motivation. And here's our rationale, right? As I mentioned several times, when you go to the field, you see what's available or visible to you, then you will be able to guess where your pipelines are. And the second part is that we, as engineers, we have some design criteria, right? So the areas we want to avoid, some specific locations and the varying depths that we all would like to follow. So these are the design criteria and the regulations. You can bring them into consideration to help your algorithm to process better. So we did a little bit, we did quite actually extensive literature review looking at the current existing methods. The finding point is that we can actually paraphrase the problem into an optimization problem while minimizing the cost while adhering the constraints. So what we are looking at is a bunch of limitations we have by looking at existing limitations, looking at existing methods, and identify the potential opportunities for us to develop advanced algorithms to make this make it work. So here's the methodology. We started with the GIS data. We extracted the publicly available GIS data and to prove the concept. So what we do is we can extract the points and the lines. That's how GIS represents the network data. And once we have that, we can capture them into features and design the model. And so here's the data model we have where we put all these data into a structured format so that we can develop our further algorithm down the road. So the specific algorithm we're dealing with is called graph neural network. So basically, again, you're looking at the points, and then you're trying to predict whether you have links exist connecting those points. So we did, this is our experimentation, the typical procedure. You process the data, you adjust or verify the parameters that you want to use, and you do hypothesis testing. So here's the data that we come up with, and I take the GIS data and extract them into the format that the algorithm can use. And then here's the architecture structure of the deep learning algorithm we actually developed. And we have several variations looking at how many hidden layers we have, looking at the dropout rates. And we also have several base models and plus some variants. So some of the partial results are illustrated over here. As you can see that one particular method shows that we get to the highest results. As you can see, I focus on recall. That's because in utility locating and detection, this domain, it is very important to not miss anyone, right? It is better to identify more than you're supposed to identify. So our conclusions and discussions here, it's still very preliminary, but we were able to integrate the feature encoding techniques and the graphical neural network to be able to help complete the topological network of underground utility networks. We can also leave out certain design criteria to reduce the misdetection. This is also a very interesting observation. It's against the common sense. So we are still trying to figure out what's the reason behind it. Our point towards that one is we needed to consider the regularization powers of different constraints. In other words, you really don't need all the constraints, but you also want to make sure that you know which ones is the best to use. Our future direction is to try to capture a spatial temporary weak or strong constraints that are appropriate in the model. So that concludes the presentation today. Thank you very much.